In section 2 of our carbohydrates lecture, we're going to cover the stereoisomers of sugars. First, we're going to look at sugar diastereomers and how we represent them using Fischer projections. The hydroxyl-attached carbons in a sugar chain are often chirality centers. This means that they can exist in two possible mirror image configurations. Fischer projections, which you might want to review from the stereochemistry chapter from first semester organic chemistry, were created to make it easier to see the exact configurations of the stereocenters in sugars that have multiple chirality centers. This is important because a sugar molecule with more than one chirality center exists as several diastereomers. Diastereomers are technically completely different substances. They also, in carbohydrate chemistry, are going to have different names and they have different chemical properties. An example of sugar diastereomers are shown below. These diastereomers are called threose and erythrose, and they are the diastereomers of the two 4-carbon aldose sugars that exist. We can see that in erythrose, on the Fischer projection, the two hydroxyl groups are both on the same side of the Fischer projection, whereas in threose, the hydroxyl groups are on opposite sides of the Fischer projection. This makes them diastereomers because, if you remember by definition, diastereomers are structures in which some of the chirality centers have the same configuration while others have opposite configurations. Threose and erythrose are examples of a pair of diastereomers that differ in the configuration of only one carbon, only one chirality center. In this case, this top chirality center. Sugar diastereomers that differ in the configuration of only one carbon are called epimers. In addition to existing as diastereomers, the individual diastereomers can exist as pairs of enantiomers, exact mirror images that are not superposable. A convenient way of indicating the specific enantiomer of sugars was developed and called the DL configuration. So here's an example. Most sugars are chiral. They exist as pairs of non-superposable mirror images, which would be enantiomers. For example, here, these are the two enantiomers of glucose, an extremely important naturally occurring sugar that is central to our metabolic biochemistry. The naturally occurring glucose looks like this. If we look at the Fischer projection, we can see that it has 4 chirality centers with hydroxyl groups on it, and the hydroxyls are arranged right, left, right, right. This is actually a very convenient shorthand way to remember the exact structure of glucose. The mirror image then would have the hydroxyl groups on the exact opposite side. So for example, the first side of the naturally occurring glucose would be OH on the right, whereas in the mirror image of that, it would have OH on the left. So you can see that in the enantiomer, it is important that every chirality center have exactly the opposite configuration. It turns out that the enantiomer of naturally occurring glucose does not occur in biological systems. We need a convenient way of distinguishing between the two enantiomers of a sugar. We will see below that Fischer discovered the configurations of the sugars by building up sugar molecules starting from the bottom. The bottom or highest numbered chirality center in all of the sugar molecules that Fischer constructed had the same exact configuration. Therefore, Fischer used the configuration of that highest numbered chirality center, the bottom chirality center, to designate its overall absolute mirror image configuration. The rule for this is fairly straightforward, but it does require us to have a Fischer projection of the sugar of interest. In order to designate a sugar as one enantiomer or the other, we first look at the highest numbered chirality center in the Fischer projection. If the Fischer projection is correctly drawn, this will be the chirality center that is at the very bottom part of the chain. We then identify the highest priority group that is attached to that chirality center. Typically, this is going to be either a hydroxyl group, OH, or some type of amino group, NH2, or possibly NH with carbon groups attached. After determining the highest priority group, we then look at the Fischer projection and observe on which side of the Fischer projection is this group located. If it is on the right side of the projection, we will call this the D enantiomer of the sugar. If, on the other hand, it is on the left side of the projection, we will call this the L enantiomer. For example, we might be asked to classify the following sugars as having either the D or L configuration. Here are some typical sugars. If we look at them then, for example, on this first one, this 5-carbon sugar with all of the OHs on the same side of the Fischer projection is called ribose, a very, very important sugar in biochemistry. If we look at this particular structure of ribose, we can see that the highest numbered stereo center, assuming that we number from the top, 1, 2, 3, 4, 5, the highest numbered stereo center would be number 4. We can also see that since number 1 is drawn at the top, it would be the chirality center closest to the bottom. On this chirality center then, we see that we have a hydroxyl group. Since all of the other attached atoms are either carbons or hydrogens, the hydroxyl group should be the highest priority. And this particular hydroxyl group is on the left-hand side of the Fischer projection of the structure. This makes this the L enantiomer. This is actually the unnatural enantiomer. In our second example, we have 3 O's. Here would be carbon 1, 2, 3, 4. The highest numbered carbon would be this carbon right here, carbon 3. The hydroxyl group is on the right-hand side. This would be D, 3 O's. Here's another example, erythrose. In this example, we can see that the highest numbered chirality center, the bottom chirality center, has the hydroxyl group on the left. This would be L, erythrose. Finally, another extremely important sugar molecule in biochemistry is glyceraldehyde. And we can see that in glyceraldehyde, there is only one chirality center. So that, by definition, will be the highest numbered chirality center. On that chirality center, in this structure, we see that the hydroxyl group is on the right-hand side. This is therefore D-glyceraldehyde. I can't stress enough the importance that if we have enantiomer sugars, all of the chirality centers will have the opposite configuration. In other words, all the chirality centers will be mirror images, or in a practical sense, all of the OHs in sugars of this type will be on the opposite side. So for example, D-ribose, which we will see later, has all of its OHs on its chirality centers on the right-hand side. That would be the exact mirror image of L-ribose. One final note, we're going to see below very briefly how Fischer used chemistry to build up all of the important D sugars starting from glyceraldehyde. He did this by building them up at the top by adding carbons to the top and creating new chirality centers above the bottom chirality center. So all of the sugars he built had the D configuration because the bottom chirality center came from D-glyceraldehyde and never changed. All of the sugars that appear in biological systems also have the D configuration. This implies that biological systems make sugars by building up from the bottom, similar to how Fischer built his sugars, which we are going to cover in the next section.